Hey guys, this is test 36 game 1. This is the fruit stand game. It's an in-out game, also known as selection. We're looking to see how many types of fruit are carried by the stand and how many are not. So those that are carried will be in and positive. Those that are not carried will be out and negative. If you look at the rules, you see that they're all conditional statements, and we have the same variables featured in multiple rules. For example, we have kiwis, K, in the first rule and the second rule. We have pears in the first rule and the third rule. We have tangerines in the second and fourth rules, and watermelons in the third and fourth rules. So these rules link together a great deal. We're going to write down each rule, then take its contrapositive and link them together as we go. So the first rule is, if we have kiwis, then we do not have pears. Contrapositive, if we have pears, then we do not have kiwis. Next rule, if we do not have tangerines, then we do have kiwis. We already have K right up here, so I'm just going to stick not T in front of that, and it leads to positive K. Contrapositive, not K, then T. Next rule, if we have O, then we have both P and W. So O requires P. Contrapositive, not P, requires not O. Also, O requires W. We already have positive O here, we just drew it, so O requires W. Contrapositive, not W, requires not O. So O to P, O to W. Not P to not O, not W to not O. Next, if we have W, then we have F or T or both. Now having or in the necessary condition is really annoying, because we don't know that W necessarily requires both F and T. We just know that it requires at least one of those two things. So to deal with or in the necessary condition, I use a dotted arrow. We already got T up here, so I'm just going to do a dotted arrow to T, and then a dotted arrow down to F. Contrapositive of W, then F or T, would be not F and not T, then not W, because or becomes and when taking the contrapositive. We've already got not T right here, so I'm just going to stick a not F above that, do a little plus, because remember, it's the both of them together that form the sufficient condition to guarantee not W. Simply one of F or T being out is not enough to require that W is out. It's the two of them together that form the sufficient condition. So this is our setup. Now if you look at it, you'll see that the bottom chain is obviously a lot nicer to use because, well, it has many more positive variables on it. It has O, P, W, T, F, all positive and only one negative, whereas the top chain has 1, 2, 3, 4, 5 negatives, of course. So the bottom chain is easier to use, and we can see that O is clearly the most powerful variable here. He's kind of like the kingpin. So we can form an abridged version of this chain and say whenever we have O, we will have P, W, and T. O requires P and W directly and then requires T indirectly by way of P and not K. So whenever we have O, we have P, W, and T. Of course, K is out as well, but this is an abridgment, a summary. Question number 1. A complete and accurate list of kinds of fruit the stand carries. Now, I just said that whenever we have O, we have P, W, T. That's our summary of the bottom chain. So any choice mentioning O must also mention P, W, and T, or else it is bad. If you look at O, choice A, we have O listed, we have P, yet we lack both W and T. So therefore, A is bad. It does not comply with our abridgment here. B does not contain O, so I'll skip that for now. C mentions O, mentions P and W, yet does not mention T, so C is bad. D mentions O, mentions T and W, yet does not mention P, so D is bad. E mentions O, mentions both P and W, yet does not mention T, so it is bad. Of course, E also contains P and K, which conflict with each other, so it's wrong for that reason as well. But our abridgment lets us avoid having to think about that. And so we are left with B by process of elimination, and B is our answer. Next, number 2, which could be the only kind of fruit that the stand carries? Well, of course, it cannot be O, because we have our abridgment right here telling us that O requires many other things. It cannot be P, because P requires T indirectly, so C is gone. It cannot be D, or could it, really? It could not be E, because W requires F or T, at least one of those two things. So E is gone, and we are down to A and D. Now F, well, that seems fine, because F doesn't really require anything else. But T also seems fine, so which is it? Well, we know that K and T, negative K to positive T, negative T to positive K, those guys have a negative arrow positive relationship. Whenever one of them is out, the other is in. Whenever one is out, the other is in. Therefore, we must always have at least one of those two, and we can never lack both of K or T. So the correct answer to this question would have to be one of K or T, and K is not a choice, but T is, so D is our answer. And while F for choice A does not appear to require anything else, saying that F would be the only thing in forces everything else to be out, which is not permitted, because then we would lack both of K and T. So A is eliminated, and D is our answer. Next, number 3, what cannot be a complete and accurate list? So this is kind of like the opposite of question number 1. Here we're looking for the one scenario that is bad, while the other 4 will all be good. Now, once again, we can use our abridgment on the bottom right here. O requires P, W, and T. Any choice mentioning O must mention P, W, and T, or else it is a bad choice. None of A, B, C mention O, so we'll skip those for now. D mentions O, yet does contain P, W, T, so that appears to be good for now. However, choice E mentions O, mentions P and W, yet does not mention T, so E is a bad scenario, and because this question is asking us for a bad scenario, E is our answer, and the other 4 choices must all be good. Next, number 4, if the stand carries no watermelons, then what must be true? So, no watermelons requires no oranges, and that's about it, and of course there's no choice simply saying oranges are out. So this is a question that appears to be pretty tough at first glance. However, we actually have a great deal of previous work, previously known valid scenarios that could help us here. From question number 1, we learned that PT constituted a good scenario. From question number 2, we learned that T alone was okay. And from question number 3, choice A, we learned that KT by itself constituted a good scenario. Now, B, C, and D of question 3 also seem fine, but they have watermelons, so they're not going to help us out here. We can look at these 3, PT, T, and KT, to help us eliminate choices for question number 4. So when we lack watermelons, as we do for each of these 3, must we have kiwis? Well, in 3A we did, but in 1 and 2 we did not. So A is not a must. Must we have at least 2 kinds of fruit? In question number 2 we had only 1 kind of fruit, so B is not a must. Choice C, must we have at most 3? Well, none of these appears to be more than 3, but that doesn't tell us whether having more than 3 is possible, so we'll skip C for now. D, neither O nor P. Well, in question number 1 we had P right here, so D is bad. Choice E, neither O nor K. For 3A, we had K, so that's certainly not a must, and we are left with C by process of elimination. Now, if you want another way to solve this question using a more deductive approach, just simply using pure logic, we could make a little in-out table here. And we know that not W, W out, requires O out, and nothing else appears to logically follow from that conditional relationship up here. However, we do know that K and P have that positive arrow negative relationship ending on a negative note, forcing more things out. So generally, always, we must always lack at least one of the KP pairing. At least one of those 2 things must always be out. So whenever we lack W, we will lack at least 1, 2, 3 things from a total of 6 types of fruit, so therefore maximum 3 in, at most 3 as choice C says. So that's the more deductive way to solve this question. Next, question number 5. If the stand carries watermelons, what must be false? So if we look at the chain here, positive W leads to F or T, at least one of those two things. Not a huge number of inferences here to get deductively from the chain, so let's use previous work once again. Remember from question number 4, we knew that from question 1, PT was good, from question 2, T alone was good, and from question 3A, KT was good. Now we're going to use 3B, 3C, and 3D, meaning TW, FKW, and OPTW from question 3, because remember again, 3E was the bad scenario, therefore those others must all be good. So we're going to look here to see what from these previous valid scenarios could help us eliminate wrong answer choices from question number 5. So must be false equals 4 could be trues, meaning that there are going to be 4 could be true choices here, and whatever remains will be our must be false. Also, we have the phrase does not carry, and that's very negative phrasing. We don't want to be dealing with a double negative here, so I'm going to change that to lacks. So I'm going to look through our choices for number 5, and if something could have happened, meaning we've seen it before, like in question number 3, I'm going to use our TW, FKW, OPTW to help us eliminate wrong answers for question number 5. So if the stand carries watermelons, could we lack figs? And yes, we've seen that for question 3, TW and OPTW. So A is eliminated. B does not carry tangerines. We saw from 3C, FKW, that we did not need to have tangerines. We could have lacked that, so B is gone. C does not carry pears. We saw from both 3B and 3C that we could have lacked pears, so C from 5 is gone. D, pears but not oranges. Well, we've never seen that happen, but that doesn't necessarily mean that it's not possible, so we'll skip that for now. And then E, pears but not tangerines. Again, we've never seen that, but if you look at the chain, we see that pears always require tangerines. Whenever you have pears, you must have tangerines, so you could never have pears yet lack tangerines. So E is our answer. Now, if you look at D, you'll see that pears but not oranges. Pears don't require oranges. It's oranges that require pears. So that would be going backwards on that arrow, not permitted, not logically valid, and D is eliminated. Question number 6, last question of the game. They're giving us a new rule. This is suspending one of the previous rules, the rule imposing a relationship between K and T. So last question of the game, it's perfectly fine to modify your main diagram if this is the last question that you're doing. So I'm going to cross off this arrow between K and T right here, as well as the contrapositive arrow. So our previous abridgment of O requiring PWT is no longer valid. That was from the previous state of affairs, the original diagram. However, we can put down a new abridgment here. While O is not as powerful as it was before, it still does determine a great deal. Whenever we have O now, we will still have, of course, P and W. And then by way of W, we will have at least one of F or T. So I'm going to put down F/T. O requires at least one of F or T as well as P and W. So any answer choice for number 6, mentioning O, yet not mentioning P, W, and one of F or T, has to be a bad scenario. And here we are looking for a bad scenario because it's a cannot question. Cannot be a complete and accurate list. So C mentions O, mentions both P and W, yet does not mention one of F or T. So C is a bad scenario, meaning that it is our answer because they were asking for a bad scenario. Choice E mentions O, mentions both P and W, yet does mention F, so it is fitting our abridgment and is good on this issue, and of course it also does not have both P and K, so it's good on that issue as well. It's a good scenario, so E is eliminated, and we don't even need to go through the others because we see that we have proof.